Here comes another surface area problem for a surface of revolution. There's going to be two differences between this one and the other example if you've seen it. This one we're going to take the function presented as y equals 1 over x, which is right here, between the x coordinates of 1/2 and 1. We're going to revolve it around the y-axis. Now it's a subtle thing here, but in the previous example we took a function of x and revolved it around the x-axis. There needs to be a match between the variable in the function and the axis of revolution in order to employ the functions that have been developed. So the axis of revolution is pretty much what you're stuck with. So that means we have to turn this function inside out and write it x as a function of y with corresponding y endpoints, so that we can then use this version of the surface area equation. So again, the axis of revolution dictates the variable of integration, and so everything else has to be matched accordingly. Now some of this stuff is easy. For example, if y is 1 over x, then x equals 1 over y, and this is gy. Okay, this will just compute it. And the endpoints of integration, well, the given endpoints for the arc of the function that generated this surface went from x equals 1/2 to x equals 1. Well, if the function is y equals 1 over x, then when x is 1/2, y is 1 over that, which is 2. And here, the endpoint here, x equals 1, corresponds to y equals 1. So the endpoints on y, they're already in the picture. They're 1 and 2, like so. Now I'm sort of slopping things all over the place here. I do not recommend that you follow this strategy. This is just scratch work, all right? But what I'm going to do is build what's in here. If we're using x equals 1 over y, then the derivative of that, g prime, is -1 over y squared, which means that, well, I'll just build it all together. 1 plus g prime of y squared is, well, this is going to be 1 over y to the 4th, and that's 1 plus that. And then the square root of 1 plus g prime squared is going to be the square root of this. Now I'm going to get a common denominator here, so this is y to the 4th over y to the 4th, so we can blend this together as y to the 4th plus 1 over y to the 4th, and that shakes out a little bit because we can let that square root do its thing on the denominator. And so when we put all this together, we will have an integral from 1 to 2 pi times the actual function, which is 1 over y, times this square root of, etc., which we just developed. And I see that this is moving off the screen, so let me see if I can adjust this. There's going to be a clip in the video. I'm going to make a bunch of moving here, and then I'm going to cut. Okay, there we go. We could tidy this up a little bit. By taking the constants out to the front of the integral and combining the powers of y in the denominator. And that is the integral that we need to evaluate to capture this surface area. This is not something we can do by hand. So instructions for this problem, which actually come from our supplemental textbook at that particular location, Chapter 2, Problem 202, that section actually says, hey, if you need to use tech, go for it. So that's what we're going to do. Okay, I think I have the screen set up so that you can see the Wolfram Alpha entry line. I've taken away the integral, but I'm going to type it in, and then we can flip back to it if we need. The integral we're going to do is 2 times pi times the square root of y to the fourth plus 1 over y cubed. That was all one big giant term, dy. And for y equals 1 to y equals 2, and we'll just check to make sure that it interpreted that properly. And it did. And it turns out it's about 5.